Non-homogeneous second-order differential equations. To begin with, hopefully you remember the techniques for dealing with a homogeneous second-order differential equation that looks like this. A, B, and C are constants, so essentially what we have is a linear combination of the zeroth, first, and second derivatives of y, and nothing else. So there are no functions of x in evidence at all. And if we write it in the standard format with the derivatives of y on one side of the equation and anything else on the other side, a homogeneous equation will have 0 on the other side. What we're going to be looking at next is a differential equation that doesn't just have 0 on the other side. In other words, there is something other than y dy by dx and d2y by dx squared. So what we're going to be dealing with is equations that look like this. Some kind of function on the right hand side. What we're going to find is we will still require all of the techniques that we've learned for homogeneous differential equations of this type, because those are going to allow us to find a general expression that creates 0, and then we're going to need to combine that with a particular expression that creates the function f of x that we're looking for. So to begin with, let's make sure we remember how to deal with homogeneous second-order differential equations with constant coefficients. Have a go at finding the general solution for this equation. When you're ready, move on with the video and we'll go through what the solution should look like. Okay, to begin with, when we're solving an equation like this, we start by finding the auxiliary equation, which is nice and quick to write down. You just got to remember that the derivatives of y get replaced with powers of something, typically m or lambda, something like that. The reason this works, if you recall, is that we use y equals e to the mx as a sort of trial function, a trial solution. And if we substitute that in, we can find that there will be solutions whenever m is a solution to this quadratic equation. So it's not the same equation, but it's called an auxiliary equation because it goes along with the original equation and tells us something about it. In this case, we get solutions, two distinct real solutions. And if you've got two distinct real solutions, there is a particular format that the solution to this differential equation will come in. So we can write our general solution as a linear combination of e to the power of 2x and e to the power of minus a half x, using the 2 and the minus a half that we got from the auxiliary equation. So remember, the auxiliary equation is produced by assuming that there is a solution that looks like y equals e to the mx, and then we can combine any solutions we find using the principle of superposition. In other words, if you've got a solution that works, you can scale it up by having any scalar multiple of that solution, and you can also add it to any multiple of any other valid solution. That gives us a complete family of all possible solutions. Remember, with a first order differential equation, we would expect one arbitrary constant, effectively the plus c, the constant of integration. But when we have a second order differential equation, we would expect two arbitrary constants. Now let's take a look at a non-homogeneous differential equation. You'll notice the left-hand side is exactly the same as the previous equation that you've just worked with, but the right-hand side is different. Now we have a function, but not a very complicated one, minus 4x. And what I'd like to suggest is that you can probably solve this by inspection. You can look at it and find at least an example of a solution to this equation. And it doesn't take too much thinking to realize that if you want minus 4x to come about as a result of combining some of your function, some of the function's derivative, and some of the function's second derivative, all you have to do is start with something linear, and then you know you'll end up with something linear. Now, sometimes it's more obvious than other times, but the beauty of this method is that we don't need to know exactly what values to put in. We just need to know what format the solution should take. So because the right hand side was linear, I'm going to use something linear as my general format. Let's see what happens. If we assume that y equals ax plus b is a solution, then the first thing I do is I find values for dy by dx and d2y by dx squared. And then I substitute those into the original differential equation. You'll notice that I'm now using an identical to symbol because the left-hand side and the right-hand side need to match for all values of x. Remember, solutions to a differential equation are in the form of a regular equation. So we're looking for a function rather than a number as our solution, which means when we're trying to find the values of a and b that make this work, they need to work for all values of x. We need to basically turn the left-hand side into minus 4x in order for this to match. So we tidy things up. We're going to compare coefficients. So I've grouped together the x terms. There's only a minus 2a x on the left-hand side. And I grouped together any constants, and then I match them up. So minus 2a has to be equal to minus 4, and minus 3a take away 2b has to be equal to 0. That gives me a equals 2, and then when I use that value of a, I can then work out that b has to be minus 3. And there we go. Y equals 2x minus 3 is a valid solution. You can go back and double check. If you double it, you get minus 4x plus 6. Or if you multiply by minus 2, you get minus 4x plus 6. That gives us the minus 4x that we need. And then taking away 3 copies of the derivative means taking away 3 copies of 2, which means taking away 6. And that loses us the plus 6 that we had before. Now, the important point to notice here is that all we've produced is essentially a trivial solution. It is one very specific function that satisfies the differential equation, but it doesn't give us a complete general solution because, well, there aren't any arbitrary constants, and I'm expecting 2 arbitrary constants. So we give this a special name. We call it the particular integral of the differential equation. Because if you think about it, the integral is equivalent to the solution to a differential equation. When we talk about a particular integral, it essentially means something specific that solves the differential equation. On its own, it's useful, but it's not enough. It only gives us one special case of the solution, and we need to combine it with a general solution to the homogeneous case to find a complete solution. Before we learn how to combine particular integrals with the other portion that's going to produce our complete general solution, let's have a go at just working out another particular integral. So for this differential equation, which once again has the same left-hand side, now I'm saying I want it to be equal to e to the 3x. I'd like you to have a go using this particular trial function, y equals k e to the 3x. See what happens if y is equal to something times e to the 3x. See if you can work out the value of k that makes this a solution to that differential equation. Give it a try. When you're ready, unpause, and we'll go through it together. So first of all, we differentiate and we differentiate again, so we can find the values of y dash and y double dash, or the first and second derivatives. Then we substitute those into the differential equation. We know that we need the left and right hand sides to perfectly match. So once again, I'm comparing coefficients. And it turns out we need 7k e to the 3x to be the same as e to the 3x, which means 7k has to be 1, so k is a seventh. And we've found a solution to the differential equation. Make a note of this. When we're finding a particular integral, we do this essentially using inspection. We look at the right-hand side of the equation, and then we choose a suitable format for what's known as the trial function. This is just the function that we try to put in. And in general, you're not going to be told what trial function to use, except in certain awkward situations where it will be difficult to spot otherwise. So in the previous case, where we had minus 4x, the trial function was of the form ax plus b. In this case, where we've got e to the 3x, the trial function is of the form k e to the 3x. In other words, it's going to be something that's the same type of function, but it needs to incorporate all the things that that function might differentiate to. That's why we didn't just use ax, we used ax plus b in the last one, because otherwise we'd end up with extra constants and we haven't got any way of dealing with those. If we ever have a right-hand side which is e to the power of something x, we preserve the value of the something. So e to the 3x is going to be produced by derivatives of e to the 3x. And so the only variation we need to incorporate is what constant we put at the front. And just to reiterate, the key issue with the particular integral is that it doesn't tell the whole story. It does give us a solution, but it doesn't give us all possible solutions. The advantage of the general solution that we were finding for the homogeneous case was that it gave a complete family of solutions. It had two arbitrary constants, so by messing with those two values, you could construct any of the possible solutions to the differential equation. That's no longer true. Now we've got a non-homogeneous version. Messing with the general solution to the homogeneous case just produces zero, and we're trying to produce something different. That's where the particular integral comes in. So each of them has its own shortcomings. The general solution to the homogeneous case gives us a general solution, but it doesn't actually solve this equation. The particular integral solves this equation, but it doesn't give us a general family of curves. Now, it's important to notice that when we were dealing with the homogeneous case and we found a solution that worked, we were able to scale it up. We could say, oh, well, if e to the 2x works, then so does 5e to the 2x or a e to the 2x. And we could add it to other solutions and so on. A version of that principle, the principle of superposition, still applies. But for this particular integral that we've found, we can't just scale up that particular integral because, well, that function works in our equation. It managed to produce for us minus 4x or e to the 3x, depending on which equation we're talking about. But if you were to scale it up, it would just give you a scaled up version of that solution. The reason the scaling worked previously was that we had equals 0. We no longer have equals 0, which means we can't scale things. We can't just tack an arbitrary constant in front of the particular integral. Which means we're going to need to do a combination of two things. The homogeneous solution is actually given a different name now that it's no longer the general solution to this equation. We call it the complementary function because it goes along with or complements the particular integral. And the trick is that we're going to put that solution, that complementary function, which we previously referred to as the general solution to the homogeneous case, we put it together with the particular integral, and it produces for us something which is simultaneously general because it comes from the general solution to the homogeneous case, and correct because it uses the particular integral. Essentially, the complementary function, the general solution to the homogeneous case, gives us all possible ways of creating zero, and then if we add on the particular integral, it converts all of those zeros to a valid solution that gives us the correct right-hand side. And that's it, essentially. We're going to add those two things together. Let's see what it looks like in practice. So the general solution to a non-homogeneous differential equation essentially means we're going to combine the complementary function with the particular integral. And I like to think of this particular integral as the bolt-on expansion pack. So maybe you've discovered that the thing that worked previously for the homogeneous case suddenly no longer works. It produces a zero in as many ways as you like, but it doesn't produce correct solutions. While this little bolt-on makes it backwards compatible, basically. So suddenly the general solution is produced by adding the complementary function to the particular integral. For example, we already found the general solution to this homogeneous differential equation, the 2 d2y by dx squared minus 3 dy by dx minus 2y equals 0. We got that at the very beginning of the video, a e to the 2x plus b e to the minus a half x. You've also correctly computed a particular integral for the non-homogeneous differential equation. Same left-hand side, but the right-hand side was minus 4x. And that gave us y equals 2x minus 3. What we're going to do now is combine those two things together, and it's literally one line. We've already found the complementary function, we've found the particular integral, and by adding those two expressions for y together, we generate our general solution. And this is a complete and accurate general solution to the non-homogeneous differential equation. A e to the 2x plus b e to the minus a half x, that's the complementary function section, plus 2x minus 3. That is the particular integral. So let's recap the overall process for solving a non-homogeneous differential equation. We begin by finding the complementary function. And remember, the complementary function of a non-homogeneous differential equation is simply the general solution of the homogeneous version. So you ignore the right-hand side temporarily, you assume it's equal to 0, you create your auxiliary equation as you normally would, and then you look through the different possible cases to construct what would be the general solution if the equation were homogeneous, but is now known as the complementary function because it still needs an additional part added on to produce the general solution to the non-homogeneous case. Just a quick reminder, these are the three different cases that you need to be familiar with, and you've got to be able to quickly and easily reproduce for yourself. The first one is where the auxiliary equation gives roots that are both real and distinct, so two different real solutions. Like the example we had earlier where we had 2 and minus a half, we ended up with a general solution to the homogeneous equation that looked like a e to the 2x plus b e to the minus a half x. Now things get a little stranger if the two roots are equal. So if you've got a repeated real root, and this produces the interesting effect that because you've only got one root, you haven't got a nice way to create two different solution sets that you can put a different arbitrary constant in front of. But it turns out in the special case where you've got a repeated root, it's not just e to the root times x that works, but also x e to the root times x. So x e to the alpha x is also going to be a valid solution in that particular case. And that means that you can just add those things together. And because e to the alpha x is a factor of both, it's often written like this. So we get our two independent arbitrary constants in the form of something linear that goes in front of e to the alpha x. And the final version is when the roots themselves are not real at all. We've got complex roots. And because complex roots to a real valued quadratic will always be complex conjugates, we think of these roots not just as alpha and beta, but as p plus or minus qi. And we can construct for ourselves a general solution that still is purely real by extracting the real and imaginary parts and putting it in the form of this. It's got trigonometry involved. Now, it's not wrong to say that the first of these three boxes is valid for all of the cases. It's just that for real repeated roots, it doesn't give the full picture. And for complex roots, it potentially gives complex results if a and b are just real constants. So we have to get a little bit creative, and we do a bit of sneaky messing around with what a and b are allowed to be. And we can extract essentially the cos and the sine from the complex number solutions that we would otherwise be given by e to the power of an imaginary value. And that's where this trigonometric result comes from. It's going to turn out to be really useful when we're exploring situations like simple harmonic motion or damped harmonic motion, where we've got something which is oscillating back and forth following a trigonometric pattern, and perhaps also decaying as time goes by because we're losing energy from the system. Think about a bungee jumper going up and down, gradually less and less. So this is quite a common one, and it's worth being familiar with. It's worth mentioning as well that you might find a fourth case described in the textbook where the roots are purely imaginary. But that's just a special case of this one. If you imagine what happens when p is equal to 0, then e to the px will just be 1, and the beginning part disappears. You can just write it as a cos qx plus b sine qx. But since that's a trivial special case of this, I don't think it's worth trying to learn 4 different results. These 3 are worth learning, and then the fourth is just a trivial special case of the third one. Now, the second part of the process, when we're solving a non-homogeneous differential equation, is the particular integral. And generally speaking, what you're looking for is a function which is in a similar form to f of x. So whatever the function is on the right-hand side, you're looking to use as your trial function something which is going to be similar. So for instance, if f of x is just a constant, then you're going to try y equals a constant. So y equals a, for instance. If f of x is linear, you go with something linear. If f of x is quadratic, you go with something quadratic. Remember, if f of x is 7x squared, you don't just put in ax squared, you also include the bx and the c, because we need to describe all possible combinations that we might get when we combine the function with its derivative and its second derivative. For the exponential version, you just have a scaled version of the same exponential. E to the something x will remain e to the same something x. Just put an arbitrary constant in front that we're then going to try to find a value for. And for trigonometric results like sine, you're going to need, once again, to take into account all possible derivatives of that function. So you're going to go with something that incorporates a sine and a cos. But if it's sine of 7x, then we're going to use sine 7x and cos 7x for our two terms. One final little bit that's worth thinking about, we'll explore more carefully in a subsequent lesson, is if your original trial function doesn't work, chances are that's because it already forms part of the original equation. So for instance, if you think back to the first example we had, the general solution to the homogeneous equation had an e to the 2x in it. That means if you try something with e to the 2x as your trial function, perhaps because e to the 2x was what was on the right hand side, you're actually going to find it just breaks apart, because putting in any multiple of e to the 2x into the left hand side will reduce it to 0. It's a special case of the general solution, so it's always going to give you 0. It can't ever give you e to the 2x. But a useful trick is to do a similar thing to what happens with the real repeated roots over on the left-hand side. Try what happens when you multiply the function by x. So if e to the 2x isn't going to work, you will probably recognize that straight away because you've already found the complementary function. You can try x e to the 2x instead. Let's work through a complete example together. With this one, we've got d2y by dx squared plus 81y equals 15e to the 3x. The first step is always going to be to work towards a complementary function, which means an auxiliary equation. It's important to remember here that when you're constructing your auxiliary equation, if there are certain terms missing, like in this case there's no dy by dx term, then think carefully about whether it's an m or a constant or an m squared that's going on. In particular, a common mistake is because we've got 81y, it's easy to assume that's going to become 81m, but actually y is the 0th derivative of y. We've not differentiated at all, so that corresponds to the constant term. Dy by dx will correspond to m to the 1, and d2y by dx squared will correspond to m squared. So this equation is actually going to be m squared add 81, not m squared add 81m. And if I rearrange that equation, I find complex roots. In this case, purely imaginary, but we can think of them using the same case we talked about before for complex conjugate roots. Because they're complex conjugates, what would be the general solution if we were just solving the homogeneous case is e to the 0x, so that's the real component in front of x, multiplied by some linear combination of sine 9x and cos 9x, 9 being the imaginary component within both of those complex conjugate roots. Because they are purely imaginary, the e to the 0x becomes irrelevant and we can get rid of that term entirely. We've just got a cos 9x plus b sine 9x. That is our complementary function. You'll notice I've labeled it CF rather than GS. I don't want to confuse myself into thinking that this is the general solution to the original equation. This is only the complementary function. It'll form part of my general solution, but it's not the whole story. Next, we look at the right-hand side because our job will be to find a particular integral. We need to look for a function that is going to be the right format. And because the right-hand side is some multiple of e to the 3x, the format I'm going to use is some multiple of e to the 3x. I'm just going to go with a e to the 3x. And if y is equal to a to the 3x, if that's my trial function, that's what the TF stands for, then I can calculate the first and second derivatives, substitute them into the original differential equation, and then compare the coefficients. I've got a coefficient of 9a plus 81a, so that's 90a, and on the right-hand side, the coefficient is 15. So a has to be a sixth, and that gives me the particular integral. You'll notice there's a lot of places in this solution where I've written y equals something, and so far none of those places have been the actual general solution, so you've got to be very careful to label them at each stage. The complementary function is y equals something involving trig, and then we have a trial function, so the general version of what's going to become the particular integral with an unknown a in front of the e to the 3x, and finally the particular integral after we've found the value of a. The last step is to combine those two. Put together the complementary function and the particular integral, so y is now equal to the sum of the two different things that y was equal to in the cases of the complementary function and the particular integral. And that's it. A cos 9x plus b sine 9x plus a sixth of e to the 3x. I want to go through is the use of all of these bewildering abbreviations. We've gradually started to drip more and more of these into the process of solving differential equations. And although you might be familiar enough with the last two of these, we've started to use a lot more. And it's important that you recognize why these are important. So on the right-hand side, you can see a solution. It's a valid mathematical solution as far as it goes, but it's needlessly confusing because none of the equations have been labeled. So I've written y equals something a bunch of times, and it's only at the very end that I end up with the thing I was asked to produce, the solution to the original differential equation. So what I'd like you to do is to get in the habit when you're solving your own and to practice it with this question, producing for yourselves not just a valid sequence of equations, but a correctly annotated sequence of equations. So go through and see if you can annotate where should the appropriate abbreviation go at each point in this solution. When you've done that, unpause the video and you can compare to mine, and we'll see if you've managed to figure out where every single piece belongs. Okay, let's begin at the very beginning. M squared plus 2m plus 1 equals 0 is an equation that appears to have popped out of nowhere. Well, it is related to the equation that we were asked to solve, but in a slightly convoluted way. The first step will be to ask yourself, well, what's the simpler but related homogeneous version of this differential equation? And from there, what would the auxiliary equation look like? So this is known as the auxiliary equation, and it helps us to determine the form that the complementary function will take. Remember, that's either going to be two different e to the power things that you add together, or maybe an e to the something and an xe to the same something, which is what this version turns into, or possibly even something with a sine and a cos, because you've got complex roots that come out from the auxiliary equation. The next equation that needs labeling is this one. This is the complementary function. Now, if the original equation had had a 0 on the right-hand side instead of 2 cos x, we'd be done by now. This would be the general solution to the homogeneous differential equation. However, this isn't a homogeneous differential equation. This one's non-homogeneous, which means the label given to this line is complementary function, not general solution. It is the general solution of the corresponding homogeneous equation, but we also need to combine it with the particular integral before it becomes a valid general solution to this non-homogeneous equation. The next bit we have down here, y equals a cos x plus b sine x, is particularly important to be careful here because this looks rather similar to the same sort of thing you might get from, let's say, imaginary roots from an auxiliary equation. In this case, though, what it represents is the trial function. This is the stage of the working out where we're trying to find the particular integral that we can tack on to the end of the complementary function. So we look at the right-hand side, which is some multiple of cos x, and we construct a generalized version of that. So it involves cos, which means the first derivative will involve sine, and the second derivative will involve cos again. I need something that has some sines and some coses, so I can find a good combination of sines and coses that will produce what I need. So this is my trial function, and it needs to be modeled on the right-hand side in order to produce for me a valid particular integral, which is what this is. So after I work through the process of finding the first and second derivatives, substituting them in, simplifying, comparing the coefficients of, in this case, sine x and cos x, I eventually produce something which is a valid solution to the original differential equation, y equals sine x. But of course, it has no arbitrary constants involved, so on its own, it's not sufficient to give me a complete general solution. However, it is the second half of the general solution to the non-homogeneous differential equation. And last, but by no means least, we have the general solution itself. This is the complete family of solutions to the original equation, and it's produced by simply adding the complementary function expression to the particular integrals expression. So the a plus bx e to the minus x gets added on to the sine x, and I've got my general solution. The only acronym in my list that wasn't used in this particular case was PS, the particular solution. And for this, you would need to be given some additional information. So with the first line of this question, solve this differential equation, I wasn't given any additional facts about the curves that I'm talking about. If they'd said, oh, the curve passes through the point 37 and also the point 29, I would have had two bits of information, boundary conditions or initial conditions, depending on what you want to call them, and we could substitute those in to this general solution, find the values of capital A and capital B, and hence produce a particular solution. But in this case, a general solution is all I need to get to, and that's where it stops. The last thing I'd recommend you try exercise 7C, particularly just the first question, maybe the first two questions. As you work through the exercise, you'll see some slightly more complex things coming out to do with the sneakiness of a particular integral not quite working. But these questions will be a good starting point because there's lots of them, and each one requires you to build confidence and practice rapidly and easily producing the complementary function using the auxiliary equation, and then choosing an appropriate trial function to produce your particular integral and putting them together to get the general solution.